In this video, we're going to look at an important corollary to the division algorithm for polynomials. So to start, I want to actually review that particular algorithm. The division algorithm for polynomials says that if f is a field and if little f and g are inside the ring of polynomials with coefficients pulled from f, then there exist unique polynomials q of x and r of x inside f square bracket x such that little f is equal to q of x times g of x plus r of x, and importantly, the degree of r of x is strictly less than the degree of g of x. This particular theorem has important implications for the kernels of evaluation homomorphisms for rings of polynomials where the coefficients are pulled from fields. I want to look at that particular situation very carefully. So we're going to let f be a field, and we're going to let alpha be any element of f. And I want to recall that phi sub alpha going from f square bracket x to f, defined by phi sub alpha of p of x is just p of alpha. This guy is a ring homomorphism. And in a previous video, we even showed that f square bracket x mod the kernel of this homomorphism turns out to be isomorphic to the ring of coefficients, which in our case is the field of coefficients f. But it turns out that when our coefficients are pulled from a field, we can go further. So in fact, if the coefficients are being pulled from a field, then the kernel of our homomorphism, the kernel of our evaluation homomorphism, turns out to be a principal ideal generated by a linear function, namely x minus alpha. And this is the set of polynomials that look like something that I'm just going to call r of x times x minus alpha, where that r of x polynomial is pulled from f square bracket x. So I want to prove this particular fact. This is going to be our corollary. And I want to use a double inclusion proof. So let's first of all show that the kernel of the homomorphism is a subset of the principal ideal generated by x minus alpha. So we're going to let p of x be any polynomial inside the kernel of our evaluation homomorphism. Now that tells me that p of alpha has to be the zero inside of our field f. Now the division algorithm says there exists a q of x and an r of x inside f square bracket x such that p of x is equal to q of x times the linear polynomial x minus alpha plus r of x, and the degree of r of x has to be less than the degree of x minus alpha. Of course, the degree of x minus alpha is known to be 1, and saying that the degree of r is less than 1 says that r of x is a constant polynomial. In other words, r of x is identically equal to some c where that c is an element of my field of coefficients. Now, if we start looking at this particular equation up here, if c is equal to 0, then we're done because p of x will be a multiple of x minus alpha, and that would put it into the principal ideal. So how are we going to show that c is equal to 0. Well, that's going to come from this fact up here. So let's put the two facts together in the following way. We already know 0 is equal to phi sub alpha of p of x. And so that's going to tell me that 0 is equal to p of alpha. But p of alpha is just q of alpha times alpha minus alpha plus our c. And now I want to think about it. Alpha minus alpha is a big fat 0, and so this equation that we're looking at implies that 0 is equal to q of alpha times a big fat 0 plus c. But that says 0 is equal to 0 plus c, which says 0 is actually equal to c. And so what does that mean? Well, let's kind of just go back up just a minute. If we know that c is equal to 0 and r of x is equal to c, that says this thing here is just a 0. And so what we now have is that p of x is actually equal to q of x. Let me make my notation look better, times x minus alpha. And that says p of x is indeed inside the principal ideal generated by x minus alpha. So we do have the kernel of phi sub alpha is a subset of the principal ideal generated by x minus alpha. Now we need to look at the inclusion going the other way. In other words, we need to show that the principal ideal generated by x minus alpha is a subset of the kernel of phi sub alpha. Now this is actually much easier than the first inclusion. Let's just let g of x be anything inside this principal ideal. That says that g of x is equal to q of x times x minus alpha. Let me make my parenthesis look better. For some q of x inside f square bracket x. So what does that say? That says phi sub alpha of g of x is going to be phi sub alpha of q of x times x minus alpha. So what we have is g of alpha is going to be q of alpha times alpha minus alpha. But this is a big fat 0 again. So we get q of alpha times 0, which is just 0. So that says phi of g of x, which is g of alpha, is indeed 0, and that says g of x does belong, let me make my notation just a little bit clearer. So we have g of x does belong to the kernel of phi sub alpha. And that's enough to say that the principal ideal generated by x minus alpha is a subset of the kernel. And with our previous work, that says the principal ideal generated by x minus alpha and the kernel are actually one and the same set. And that ends the proof. Now, I do want to say one more thing about this corollary. This corollary actually says something else. This corollary says that p of alpha is equal to 0 if and only if p of x belongs to the principal ideal generated by x minus alpha, and that happens if and only if x minus alpha divides the polynomial p of x. In other words, alpha is a root of a polynomial p of x if and only if x minus alpha divides the polynomial p of x. But in order for this statement to be true, we must have p of x belongs to f square bracket x, where the ring of coefficients is actually a full-fledged field.